Good morning, everyone. Thanks for coming. My name is John Bandela, and me and my co-author Chris are on this presentation. Chris was unfortunately, or fortunately, unable to be here for this presentation. He's actually on his anniversary trip with his wife in Italy and sending some beautiful pictures of the Italian coast. But anyway. All right, so we are going to talk about Rappel, compose algorithms, not iterators. All right, so I want to do a little bit of history. So this was an article, I believe, in the ACM from back in 1986. This was by John Bentley, and he did a regular column called Programming Pearls. So 1986, that was, I won't give away my age, but I was very young then. I wasn't doing C++ then. And he gave a challenge, right? And what's also interesting about this, he's got special guests, Don Knuth and Doug McElroy. So he's given a text. So the challenge is, you have a text file and an integer. Print the 10 most common words in the file and the number of their occurrences in decreasing frequency. Have anybody heard of this challenge before? Okay, all right.
It's a setup, it's not fair.
Don Knuth, he does an absolutely virtuoso job of using literate programming and his language that he developed called web. Like, it is beautiful. The Pascal code is elegant for being able to sort everything. He uses tries. It's beautifully typeset with cross-references and indexes. It is a work of art. Doug McElroy produces this, right? And pipeline style, right? Like tr, sort, unique, sort, sed, and we're done, right? So ever since that style, right, like we've been looking at the programs have been interested in what I'm going to call a pipeline style. I've heard like different terms for this, and there's different things. For this purposes, we're going to call it pipeline style. If anybody's got like a better suggestion, let me know. So basically what this consists of, it's writing a series of transformations as a single expression without using like intermediates or nested parentheses. And it's different from the regular program style, just having like deeply nested function calls. It's common in other languages. Bash, we saw with the pipes. F# uses, I believe they call it the pizza operator. I think there's one proposed for C++. The primary syntactic feature is not so much the exact operator that you use to separate, but the lack of unbounded nesting. All right, so let's look at some C++ type pseudocode, right? So standard C++, non-pipelined, right? You take a result, call F1 with some input, get a result, call F2 with result 1, get result 2, and so on. Or else you can pipeline and get the final result without the intermediates like input, pipeline to F1, F2, F3. Any questions so far? All right, and again, I want just so we're all on the same page for this talk. The whole thing is the pipeline, so the entire series of operations that we're doing, including the input and all the processing stages. Then for the individual elements, we're going to call them a stage here. And that's each individual component of the pipeline, F1, F2, or F3. And these are all called stages. I've also seen the term combinator used for this, but I've heard some pushback about is it really a combinator or not? And so we're just going to use stage. So we have pipelines with like stages of a pipeline. Any questions?
So the input is not a stage?
Input is not a stage, correct. And with C++ 20, one of the biggest features, probably one of the biggest language features since C++ 11 was the introduction of STD ranges, right? So STD ranges does a lot, right? There's a huge amount with like concepts and like trying to normalize some of the stuff, put concepts, make it more formalize some things. But a large part is the views part, right? And the big part of that is being able to compose. So we can take like an array of integers, and we can have 2 lambdas, even and square. And then we can compose them, right? Like using range 4, ints, we pipe to std views filter, and then transform, square them, and then std cout I. We output them. right? So we don't have the intermediate states where everything is just flowing nicely through. Any questions so far? Okay, let's do a little bit more complicated example. So this one, we want to be a little bit, our job is to find, hey, is there, what integers, when we cube them, are greater than the hash of them converted to a string, right? Totally fine, I mean, just totally arbitrary. And we go, std views iota. Iota is like it's like a input range that starts at 1 and counts up to, but not including that last number. So from 1 to 1,000,000, we transform, we make the int and string. So we're just aliasing an std pair. We should probably use a struct, but we're just going to use a pair here. And cube the 1 and convert it to a string. And then our next stage, transform uses std invoke. So we can pass and invoke any invocable. So we can just take the address of int and string second, and we take the first 4 elements, and then we iterate, then output. Anybody know what's the first number printed? Any idea?
1.
We actually crash. All right, why did we crash? Go ahead.
It overflows int?
We actually don't overflow int. 1,000 times 1,000 times 1,000,000, so we're 1,000,000,000. So int 32 should be.
Times 1,000,000 times 1,000,000.
Actually, you're right. Okay, we overflow. We actually crash before we overflow. Good point on that one.
The dangling string. The address of?
Yeah, we're dangling. So let's zoom in here. So the other part was just filler to hide what was going on there, right? The two main interesting things are std views transform, the make int and string, which is constructing a pair and returning it, and then the std transform. So let's reduce this down, right? So let's just focus on the std. We get the same thing: transform and make int and string, and transform second. And let's kind of manually expand out what's going on with the iterators, right? So the make int and string operator star is returning an int and string by value, so it's a temporary, right? And the second iterator is taking in, it has the int and string iterator, it's returning the second. So it's returning a reference into an element of a temporary. Everybody see that? Right, and this is tricky. The code looked fine, right? Okay, this looks normal, and then boom, we've got a dangling reference. And that's what that one is doing. And if we inline everything, it becomes even more apparent, right? Construct a temporary and return by reference an element of that. So that's one of the things. It's it was really easy for us to get us into that situation with composing ranges. Let's look at one other thing. Anybody heard of this acronym? TPOIASI. So one of the things about C++, if you ever want a concept to be famous, you have to come up with a horrible, non-pronounceable acronym, right? Like RII, SFINE, right? If we didn't have SFINE or ADL or whatever, one of those things, we won't note as much. So TPOIASI stands for the terrible problem of incrementing a smart iterator. And there's actually a Go link in Google for Go TPOIASI. So there's a Fluent CPP. It's from Fluent CPP, and this is the example. So we're doing some transform and a filter, right? So we have a numbers. We're going to multiply them times 2 and then filter to see if they're multiples of 4. So we run this, and we get output of 4 and 8. Hey, everything seems good, right? 1 second. Let's go back and augment that times 2 transformer, right? The transforming function. We're printing out 2 twice. Right? It's running the transform on twice, and for 2 twice, and we're doing 4 twice. And it turns out the filter iterator actually has an embedded loop in it, right? So every time you increment the iterator, it has to loop through the one in front of it and find the one that matches. And then it stores a reference to that one. And then when you dereference it, it calls the transform again to do it. So that's why it's getting called twice for each thing that happens. All right, so it's easy. So with ranges, when we compose them, we have two problems so far. It's easy to leak dangling references. And we have the issue of our transform functions can run more than once. And same with filter functions, anything up the stack. Let's look at what kind of stack size we get. So let's say you put 7 filters, just arbitrary, 7 filters in a row. What does this look like? And and this is main 7, and we'll look at for different numbers going through. So we do, we just do main 0, which is we don't use it at all the way up to main 7. We just have, each one has more filters in it. Here's our output. So pay attention to the third column, so the 144. So 0, our stack size is 144, 192, 240, 320, 448, all the way up to 1120 with 7. So I talked with Richard Smith about this, and he actually came up with a formula. We are 144 plus n plus 1 times n plus 2 times n plus 3 divided by 6 plus 2n times 8 bytes. Right? So we are growing, every time you add a filter, you're growing cubically. Right? And so, if you're growing at n cubed, you will grow pretty quickly. And you can easily run into especially if you're at the end of a long call chain, you can run into stack overflow issues or other things with large sizes. So what if we rethought how to compose these operations, how to compose these transformations? So we have what I'm going to pick on kind of like use 2 headers in the standard. As kind of stand-ins for each approaches. So we have iterator, right? And iterator is what we know and love. It's super flexible. That's what ranges is built on, and it has certain characteristics. It's lazy, right? Like we can construct an iterator, and until we actually iterate or dereference, it doesn't do anything. And then it's pull, right? The way you get it, when you need something, you pull a value from it. And if you have a composed iterator of ranges, you're kind of pulling from the bottom value. And so what this does is this places our loop at the bottom of the transform. So you at the bottom of the transforms of everything that we do. So our loop is on the bottom and we're pulling from the bottom. The other thing they have is they're interactive, right? We can take an iterator, we can pull one element, go do something else, even pass it to somewhere else, later on, pull another element. Hopefully it's not dangling, but that's a different story. But we're super flexible. We're iterative. We can pull one element. We can pull 2 elements. We can, not pull any elements. We have all the control is on the pull side. And we use return to transmit the values, right? Like operator star, it returns. The dereference operator, it's returning whatever the value is that we want. The other alternative, though, is algorithm. So here's the thing for SCD transform. So a few things to note. First of all, it's eager. Once you call SCD transform, by the time of the closing semicolon, it's done. Like it's run through everything and it's transformed, right? It's not lazy, like you call transform and bang, it happens. It's push. So there's a loop at the top that loops through all the iterators and pushes down the iterators through the transforms. It does it in batch. You do the whole thing, and when you specify what you want, and you're going to get the whole thing that happens. And the other interesting is its continuation passing style. Who's familiar with continuation passing style? All right, so continuation passing style is how to return data or values from a function, right? The normal way is to do a return statement, right? Where we return and we return out of it. And with continuation passing style, instead of having a return, what we do is we pass in another function that we wanted to call with the value. that we provide. And it's used a lot in functional programming, things like that. Does that make sense? So how is this continuation passing style? Well, it turns out that the output iterator is basically just a thin wrapper on a function, right? We just call it weird. It's just, dereference operator equal, right? It's got almost the exact same semantics as if you actually called the output function with that. So output iterator is basically an output function. Sorry, we interrupt this presentation with an important announcement from our sponsor. Do you or your friends mainly use ranges to iterate with range 4, pass to an algorithm, or construct a collection? You may be paying too much for flexibility. All right, so the premise of this talk is, can we give up some of the flexibility of iterator in exchange for safety and efficiency by going with more of an approach of algorithm, right? And first of all, I want to look about the return versus continuation passing style. So look at this iterator, right? So we call it iterator. It's using return. Is this safe or unsafe?
Unsafe.
Unsafe, right? Like we're constructing a temporary and we're going to dangle that, right? So return, like it's unsafe, right? We're going to do the algorithm approach. We're using continuation passing style, right? Instead of returning, we're going to take in an F. Safe or unsafe?
Safe.
Right? Because we're doing it, right? Like we're continuing to pass it on. We're not dangling anything. We're preserving the reference. The temporary is preserved, and we pass it down the stack. So how many of you came here on a flight into Aspen? All right. So as I was flying, I came to this realization. Lost luggage is a dangling reference, right? You have the ticket, you have the reference, but the luggage to which it refers is no longer with you. Everybody agree with that? Anybody disagree? All right. So landings, like returns, are an opportunity to dangle references, right? Like if you want to fly somewhere, you want to go nonstop, right? Because every time you land, every time they shift the luggage around, that's another opportunity for you to lose your luggage, right? So every time you return out of a function, every time you're switching the stack pointers and all the rest, that's an opportunity to dangle something, right? So if we can keep stuff in the air longer, do more nonstop flights, we can make this safer. Does that make sense? So a library that explores this is Rappel. It's Google's alternative to STD ranges. It's based on the eager model of algorithm, and it passes each value through a series of transformation using continuation passing style. And we've been using this since July of last year in general use. So I just want to look at some quick examples. I'll go through in more detail later on just what this looks like, and we'll look at what happens. So the crash example. We do the transform, filter, transform. We take the for, and with the for each, instead of doing a range for, we actually have a function for doing for each. And our output turns out it's 1291, 1292, 1293, and 1294. It probably changes with your standard library. But it works. It doesn't crash. We have pretty much the same thing. We're not trying to do anything fancy. We're not trying to guard against it. We're just writing our transforms as we would just in this framework, and we don't have the problem with the dangling reference because we're using continuation passing style. Let's look at TPOISA, right? Same thing. We have transform, filter, and for each, and 1, 2. 4, 3, 4, 8, 5. So each thing, our transform and filters are not repeatedly evaluated. And this allows us actually to make our model simple, right? There's a lot of kind of filters and transforms that we don't want to be called multiple times, right? Maybe they have some state with them or whatever. We can actually use stateful filters and stateful transforms with Rappel. Let's look at stack size. So same thing, we have some output. We do Rappel 7, main 7 filters, and output to STD vector. What do our numbers look like? 112, 112, 128, 128, 176, right? For Rappel 7. And just for the fun of it, I did 14. We're at 320. So we're scaling linearly as expected, right? I mean, we expect that the filter takes up some space, because we need to store, what function we're calling and everything, but we're not growing, cubically. Let's look at a couple of benchmarks. Again, there's Mark Twain said there's lies, other lies, and benchmarks, so take everything with a grain of salt. So we're going to do this handwritten loop, right? Where it's halfway done prime sieve, right? We're just going to test 2 through 11 and then just add it to a vector, right? So this is our handwritten loop. This is how we do with STD ranges. I didn't have access to doing this comparatively with C++23. I would have used ranges 2. Instead, I just made like a little lambda to call vector r.begin, r.end. So same thing there. This is the Rappel version to STD vector. And this is the optimized, right? Like this is a log scale. So this is actually very comparable. Rappel is comparable to the handwritten loop. And it's about maybe 4 or 5 times faster than the STD ranges thing. Again, like this is kind of pathological cases, a lot of filters through there. We're not doing anything expensive in each of the individual operations, but this is just a kind of measurement. This is optimized. Now you had to be careful with optimizations and micro benchmarks because especially with this thing, we're using it at the bottom of a loop, right? We're using it for a very fundamental concept. We're using it for the loop construct, right? And so where we're using it might be in a leaf function somewhere or in there in the compiler, it might not optimize as much as it would in it might not optimize a real life program as much as it would a micro benchmark, where that's all it has to do. So let's kind of look at like a worst case thing, right? So this is running with O0, no inline, right? And it's kind of like, the performance won't always be like this, but this is, okay, how deep is the abstraction efficiency well that the optimizer needs to pull us out of? So in this one, Rappel is about 4 times slower than the handwritten loop, and ranges is about 12 times slower than the handwritten loop. And again, like this, if you're running a debug build, for example, it may make a difference in terms of your unoptimized speed. It may make the difference between whether it's buildable, whether it's debuggable and runnable, or actually not.
Wait, is that a log scale?
It's a log scale. Yes.
So, filter is kind of famous for having some certain design problems. How much of these is due to that, like caches and things like that, rather than the design or the philosophical thing?
Correct. Yeah, I mean, filters is probably like the worst case thing, right? And I was doing that. But the thing is, filters is a reflection, right? But filtering is a very fundamental aspect. It's one of the core. It's one of your core parent algorithms of stuff, right? Almost everything is either a transform or a filter at some level, right? When you're processing, right? And so if we have an abstraction that makes filter inherently inefficient, right? Like, doesn't that make you a little bit worried? You know what I'm saying? So, and I think part of it, like, because of the way it's pull, right? So every single filter has to have a loop that pulls from the one above, right? By pushing, we can just, and I'll have an example of like where we kind of implement filter. We loop once, and everything is just an if statement all the way down, right? And like I said, filter is a fundamental, it's a fundamental operation. It's the basis of many other operations. And so, we should make that efficient. But yeah, you do have a point. Like, by the time you're adding expensive stuff, like you're doing like real world life stuff, and you may not have 7, 10 filters in a row, right? Sorry. Like I said, this is a pathological case. So I'd like to dig a little bit more into Rappel. Anybody remember this blog post by Eric? So Eric, when standard ranges made it, so he's got this running thing with Bartosz about doing Pythagorean triples, right? And he's been working on that and showing like how to do it in standard ranges. So we're going to Pythagorean triples, like come up with something that shows the Pythagorean triples, right? From elementary school, a squared plus b squared equals c squared. So we'll just go quickly over the STD ranges implementation. How many of you are here for David's talk yesterday? All right. Thank him for this being a little bit more painful. Maybe view, he specifically kept it out of the standard, or else they would have been maybe view in here. But anyway, so this is how you implement maybe view. So basically you have a little helper range that either 0 or 1. And then you have some helper lambdas, like a for each lambda, and then you have a yield if. And the whole point is you just try to get the general gist of this code, but you don't have to go to everything. And then we have lazy triples, right? This is the implementation. A couple things to note. It's not so much pipeline style anymore, right? It's pretty nested. Secondly, it's continuation passing style, right? Like the outputs are like the output function is being passed, to each thing. Like we're not really using returns as much. Like it's there. So it's interesting. Like we're kind of, when we actually want to do something complicated, we're going back to the, continuation passing style and passing, functions down. And if we output, like it produces a triple, and we can take the triples and take 10 of them, and we can output this. Here's how we do it in Rappel, and we'll go step by step. So everything is eager. So everything runs through apply, RPL apply. Every time you want to do a pipeline, you do it through apply. And we have iota, which is similar to STD ranges iota, just a generator, starts at 1, counts up. Zip result, what it does, it takes one of the arguments that we have and constructs another argument and returns it, and both of them get passed down through the next to the next element of the stage. Flatten, what flatten does, it takes the last argument passed, the rightmost argument, flattens it, means it like iterates on each element of it and combines it with the previous arguments and passes those to the next. So by this time, for the zip result, we've got 2 values now, int C and A. Does that make sense? We flatten them again. So now we've got C, A, and B. And now we can pass them to a filter, and we just filter return A times B times C. However, they're in the wrong order, right? We'd like it to be ABC instead of CAB. So we can swizzle the arguments, right? So 1, 2, 0, right? We just change the orders. We take 10, and we just output A, B, and C. Any questions?
I didn't quite follow the flatten.
Which one?
The flattens, what are they doing there?
So without flatten, would zip result need to receive a tuple?
The next one doesn't return so tuple. So zip result is returning a generator. It's returning C and iota. We don't want C and iota, we want C and the result of iterating iota. So you want the integers from the iota, not the actual, the range itself or the generator itself. Does that make sense now?
So,
Uh-huh.
what does take do?
Take just takes 10 items, like take 10 items. Yes. Any other questions?
Okay, so
Uh-huh.
again, about flatten. So in this case, flatten received, the first flatten received an integer and a range, so it sort of like copied the integer for each and every element of the range.
Correct.
And so if it would have received 2 ranges, would it have done a
It just does the right
much
most.
easier product? Okay. So
It just does the right most. It always does the right most. Go ahead.
Just to go back to that code, so if I'm understanding correctly, it's like A is always less than or equal to B, which is always less than or equal to C, right? Because of the way you did the iotas?
Yes.
Okay, cool. Yeah.
So if you notice here, we've got some repetition, right? We zip result, flatten, zip result, flatten, right? So, DRY, don't repeat yourself. We can use compose, right? We can call zip flat that takes a lambda and and we call compose. RPL compose, all it does is like put, two stages together and treat it as one stage. And it's basically just a simple wrapper over a tuple. So we zip result with the F and flatten. So then we end up with, just gonna go back, zip flat, right? So iota, zip flat, which, gets the iota back, flattens it, and then, does it twice. So now we have CA, then CAB, and then we continue on. However, the whole thing is very inflexible, right? Like maybe we want to take 11, maybe we don't want to output, we want to do something else, right? Like the whole reason we're doing this instead of just writing a for loop is so we can use it in other places, right? And we haven't been able to do that. So how do we do that? Right, so we want to do that. So we look at our output Pythagorean triples, and we have it return an auto, right? And Pythagorean triples. So instead of outputting, we want to return something. And then instead of apply, we want to compose, right? So we're going to, instead of applying all these operations, we're going to compose these operations. And then these parts, the ones, where we take the 10 and, the specific parts, take 10 and then output them, we're just going to delete that. So then we end up with Pythagorean triples like this, right? So zip flat, iota, and if you look, it's interesting. It's like very similar to Eric's code and like what we normally want to do, right? The first thing, iota, get all the potential values of side C, right? Get all the potential values of side A, get all the potential values of side B, make sure A squared equals B squared plus C squared. Put them in the right order, right? And then from then on, we can do it. And then say we wanted to like collect a vector of these. We can just say apply, call our Pythagorean triples, so we take, that returns the composition, we just pop it into apply, and we take 100, make the tuple, output to a vector. Any questions on that?
Why don't you need the types on the vector?
What is it?
Why don't you need to specify the vector types?
It can deduce it because it knows like what types are coming through, so it'll figure it out. Go ahead.
So apply is eager,
Yes.
and compose is not. It's just
Later.
creating an algorithm out of other algorithm.
Yes. Yeah, so we explicitly separate those into two different things, right? We have a compose that's, all it does is build our block of what we want to execute. But when we actually execute it, and you supply it with real data, we're eager. So I want to talk a little bit about Rappel, a little bit more in detail on the background. So the terminology, we already talked about pipeline and stage, right? So what I want to talk about is processing style. And this is how a stage processes elements. And we're trying to generalize this, and we came up with two kinds. There's incremental, and then there's complete. So an incremental processing style is we're processing elements one at a time. Filter and transformer like that, right? Like that you can decide, you can filter an element or decide or do the transformation one element at a time. We don't need to wait for any other elements to arrive, right? And then on the other hand, we have complete output. And that was, we want to process a single element, not as a group of individual elements, but as a whole, right? And so sort comes to mind, right? Like you need to sort the whole thing. You can't just sort one at a time. It doesn't make any sense, the whole thing. Another surprising thing is max, right? Like the maximum element. You're not treating it as an element so much, right? It's just the value of everything combined. All of, any of, none of, those are all kind of like complete processing, right? And it's not so much the type of things. For example, SCD string, right? You can either treat a string as, the whole thing itself or as a container of elements, right? And it's not necessarily the type, it's like how you're treating it, how you're doing with it. Like whether you look at it incrementally, element at a time, or more holistically and complete. Ranges v3 has this concept called actions, which are kind of like this. There's an action sort. The actions didn't make it into the STD ranges. We just got the views part, but not the actions. So everybody got this distinction between incremental and complete. And the reason is we want to, like in our pipeline, we want to be able to transition between those two. There's a lot of times we want to filter and transform some input and then collect it and sort it and maybe take the top 10 or do something with it and then move it on to the rest of our stages. And we don't want to like break our pipeline in half just to, hey, we have a side just to sort this. We want to do it all in continuously. And input and output processing style, like they don't have to be the same, right? You can have incremental input or incremental output, and there's 4 different combinations. So incremental is filter and transform. They take an element at a time and release an element and output an element at a time. Incremental to complete, if you want to collect it into a vector, right? We take an element at a time, collect it into an STD vector, output the whole vector as our result. Max, any of, all of, none of. And the generalization of this pattern, incremental to complete, is accumulate, right? That's what it does. It takes one at a time and accumulates into some type of whole. Then we have complete to complete, sort, partial sort, nth element. We need to consider the whole thing. We can't, you can't like, hey, we're good because we may have got the lowest element on the next one, right? So we don't know. So that's complete to complete.
Unique.
Go ahead.
I think unique is incremental to number. I'm not sure.
Yeah, unique, I guess. So actually, yeah, it was first initial modeled on that. There's also, we added like a filter duplicates, which is incremental. So it does the same thing. Unique, I think, was kind of like it chopped up the range to called STD unique on it. But good point.
Why isn't nth element incremental?
Because it needs to sort it, right? Like the nth element as in the partial sorting one.
Yeah, I was thinking different.
Yeah, good point.
John?
Uh-huh.
So this is implying that there must be a one-to-one either from the complete. You're either doing a complete, or if you're doing incremental, you always have one. So I mean, because like couldn't max be incremental? It just waits until it just accumulates and waits until the end and pops out the max. If it was stateful.
Like a stateful incremental. I guess part of the reason, it was like kind of like how do we compose these and put rules on it? And I'll go over that and we can revisit that. But that's a good point. So these are the rules for incremental and complete. So the processing style of a stage, the input processing style of a stage has to match the output processing style of the previous stage. Does that make sense? I just, Lego blocks together, right? The only thing is from from complete to incremental, like that's just iterating a range, and we can do that implicitly. Like, so we have a vector and we have a filter, we say, okay, this is a vector is a complete thing, but we know how to get from complete to incremental, we just iterate it, right? So, early in the design, we had a way that was explicit, but more use cases, like we can just make that incremental. There's really no cost to doing that.
So I assume there are 2 separate stages that will be transformations between these two?
The stages themselves, the way they're wrapped up, it does the transformation automatically.
Well, if you have an incremental and you want to plug it into a complete, can you just is there one that will go from an incremental to a complete?
Yeah.
You just keep grabbing stuff until it comes and then pop it through?
Yeah, for incremental complete, yeah. But you have to do that explicitly because a lot of times you're allocating memory for that, like to vector or something. Whereas you can go from complete to incremental, you're usually not allocating any memory, so we can do that implicitly. So this is apply. So the first parameter is like a range, then one or more stages. And then note the return type is auto, right? Like we don't want to return a reference. We want to return like a value out of this, right? Like we want to try to make this as safe as possible. So, once you do everything in here, values come out at the end. Basically, we want a fume hood, right? Like whenever you're running a pipeline, you're going to have all these dangerous intermediates, right? Like R-value references to temporaries are dangerous, right? Tuples of R-value references temporary are really dangerous, right? We don't want them just floating out in the code, whoever, do a dereference an iterator and get this, and it can be dangerous and scary, right? But they're useful, right? We need them for performance. You don't want to make copies all the time. So what we do, we isolate them. So basically we have this fume hood, we have this firewall, this safety that within apply, we can have all these references, the temporaries, and all these flowing through. But but by the time the user gets it, we've condensed it down to an auto. We've got the final product. This is all being done, safely.
I have a question. On the where you had that whole thing where you were iterating over the Pythagorean tuples, you convert it into tuple, and then at the last stage you convert it into vector. Vector makes sure that it's not a reference to the temporaries.
Right.
But tuple, if we directly return, there are chances that even we are returning tuple by value, it can be.
Yes. Good point. You're talking about
The make tuple. It can have references to temporaries. The tuple in temporary.
But the make tuple, like same with like std make tuple, it condenses all the references. It does values, right? Like so if you call make tuple with, even if you pass in references, right, it returns like the values of those. All right, so let's do a little test, right? See if these all go together. So apply Vmax, good or not? So we have a V starts off as a complete. We have the implicit transformation incremental, and then incremental to complete, we have a complete output. How about this one?
It ends with incremental.
Right, so that's an error. That's good.
Can't go incremental to sort.
Correct, now it's complete, so we need to do this one. Convert it to a vector, and then we can sort. And then you can go back, you can go to complete and then down and back again, right? So you can, so first of all, does this work?
I think so.
Yeah, so it will sort, filter duplicates, accumulate, just by default, we'll just add everything together. So you'll just get the sum of everything that's tripled and filtered and sorted. Any questions so far?
What's the error look like if you get it wrong?
So we've tried to make it a little bit better. There's some little traps in here. It was really bad at the beginning, right? Like we were getting messages like, what is this? And like, what's painful, it overflows like your terminal buffer. So you kind of like had to look at the log output to see like what the error was. And we've been working on making it better. There's a place where it explicitly goes through and walks and checks and static asserts, but yeah, good question. All right, compose. So we create new stages just by composition, right? It's just a thin, and compose is actually, we kept it kind of simple, right? It's just a very thin wrapper over std tuple. We just store it in there, and it's applied that does the, transforms compose into like this, pulls out the stages and puts them in as if it was actually, they were passed in. So let's look at some of the stages. We'll go kind of quickly just to show you what we have. I don't want to go on detail at it. But I do want to note that we kind of aim for default safety. Like, for example, std like max, if you pass it an empty range, it's what happens? Undefined behavior, right? And the number of times where you can get what you want, especially when you're running these pipelines and like you can hit an empty range is a lot, right? Like, so we have max return an optional t. And and part of our thing is we never return references from apply, right? So yeah, we do an optional t, and so it's safe by default, right? 1 second, partial sort, right? Like it takes 3 iterators, right? The std partial sort. So it actually takes the middle not as an n, but as an iterator. So if you go like begin plus end, you can have undefined behavior if your range is actually less of a size than n. And again, you don't want to be keeping track of that in a pipeline, right? Like, who knows what your filter did, right? Or if you're filtering against something that was user provided, like what element, right? You don't want to have another check. Oh, am I good? Like, so just n just does the right thing. Like if it's n is greater than the size, it just, it'll pass in begin end to end and just be done with it to partial source. Same with nth element. So the idea was kind of to step away from this, say, let's try to make this as safe by default as possible, right? The pit of success. So using it as you normally think, you'd end up with something safe. These are complete transformations. I'll just go through just mainly to show that although we give up some of the flexibility with iterators, we can basically provide everything that they have here, everything that ranges can do. And then we have flat map, some higher order ones.
Sorry, flat map, not in the C++.
It's not in the C++23. We added ourselves. Yeah, we just added a stage for that one. And it can output 0 or many results. Go ahead.
Can you pass an optional to an incremental?
A what?
An optional result of a max, for example, to an incremental. For example, if you want to transform.
Yeah, I'll show you some examples with optional. I have some later on ones. And then sequence extension. We have some stuff for error handling I'll talk about more. Let's see, we're at an hour. So any questions so far? And now we're going to start delving in. There's going to be a lot of simplifications and hand waving, just to note.
So,
Go ahead.
before I pay too much more attention to the rest of this, I assume this is available for us somewhere.
It's not yet. There's so right now, we don't we'd like to open source this, but we don't have the resources that that justify the business value of this. Because open sourcing stuff is expensive in terms of maintaining, and we just don't want to throw it over the wall and just whatever happens. So we're evaluating this, and any feedback is for this would be appreciated. Go ahead.
So you're creating these chains as like variadic arguments to apply or to compose, not using some inference operator like the Python,
Correct.
etc. Could you talk a little bit about that, about this design decision?
Sure. Part of those was two reasons. One is we wanted to make everything call a function to do stuff. That was kind of the output, especially with apply. We wanted a definitive time when this runs and then this state when it doesn't run. The second is operator overloading, especially with a common operator. It can there can be tons of overloads for this, right? And so, by doing this, the compiler doesn't have to look up a million places. I think there's special processing for the cout left shift operator, just because everybody overloads it, right? And so it's the pipe operator, there's expense. So because of that, we kind of did it. And then the other thing is, it's kind of nice for apply, as it lays out everything, to be able to see at one time everything that was passed into it. Like the whole thing. So what we have is this stage impl, and each thing writes it. And basically, for incremental, we need a thing called process incremental, which takes an input type, and every input type that it takes, we're all references in here. Everything is using references. And then we have, we take a template next, which refers to kind of the next stage in the process. So that's if you're incremental. You can take an optional incremental input, can take an optional end, which tells you, hey, I'm done with everything. Which is what accumulate, right? Or not quite accumulate. Yeah, accumulate can say end. Okay, this is the last one you can do stuff. And then done says, are you done? So we can break early, with take. After we're done 4, we can say, are you done? And then for complete, we just have process complete, which processes it and takes it on to the next one. So let's just look at an example for transform complete. So we just store the F, the transformation. And then this is just continuation passing style, right? We just call next process complete, invoke, and we correctly correct the static cast the input type to the input. So we preserve all values, L values, all of that goes through. So that was complete transform, incremental transform, same way. We just have different things we call filter, if, invoke F, do that, right? There's no loops, simple, right? it's about what you'd write as, if we're doing it just with a little bit of verb pool. Then when we hold things, this is where it gets tricky. So basically, we hold things in like a tuple-like structure, right? Where we have something that inherits from a bunch of holders, right? And we specify the index. So we have this overload for get index that returns this, right? So then we can, get which stage we want by index. And then we just kind of, for these optional, we just check if they're implemented by the stage or not, and we have a default implementation. And then we just pass it on to the next one. For process complete, if we're incremental, we do like a range for, it's not exactly that, but more or less we iterate on it and we call process complete on the stage that we're holding. And then chain is just, it's kind of like the CRTP we inherit from each of the holders. And then we overload, then we do like a using to bring all the gets into scope. So then when we do process complete, we can have a process complete and overload the get for the index size of, and then we can get the last one. So when the last one does it, we can just, we just bounce back and return. And then apply is just basically makes this big chain of stuff, gets the first stage and calls process complete on it and returns the value. I just want to talk about composition. So composition is the first thing you were talking about, optionals. So we can write a flattened optional, right? Compose, filter, deref. And then std vector, flatten optional, and we can just treat the optional as if, it was like no elements. Go ahead.
So iota, for example, it starts so they apply calls process complete on it, and
It passes it to process complete.
and the process complete of iota.
Yeah, there's a way to iterate. It knows how to iterate iota generator, like the incremental to the complete incremental transform, right? It knows how to iterate that one. That's kind of like special built in. And so we can have, flatten optional, right? Flatten optional, and then we can filter out optional. This is a very useful thing to have because sometimes you may have optionals. We can compose with generators like we did with the Pythagorean triples, like we did with the perfect squares. As long as the first thing is something that you would normally pass to apply and it's composed at the first position, it'll work. We can compose ranges, SCD cref, return it, like if you're returning transactions, that are all greater than 0. Generators.
With that example, the lifetime of the return compose is bound to the lifetime of transactions? Question mark?
Correct, yes. Go ahead.
So are the chains monadic? Like if one element returns optional of t, and does it?
Hold that thought.
Okay.
Yes. The answer is okay. Iota, it's a pain to write input iterators. We have libraries to help us write iterators. So we came up with this generator thing. So Iota can be written like this. Return a generator with a lambda, and it takes in an output, and we can only call it once, move output, ++ begin. If we don't call it, like here, where we have the end, if we don't call it once, it knows we're done. So, the idea was try to, kind of simplify this. And that one's been evolving more. Multi-argument streams, I think this, because we're safely containing the temporaries, we can do stuff that would be crazily dangerous, like if we had tuples of references floating around. And so we actually support multi-argument streams, and they actually use a different type other than tuple that's non-copyable and non-movable, so you can't just store them in a vector right at the end. We don't want you to do that. So we take a pair of int vector, we can expand the tuple, flatten it to int, and do a for each. And then we, first class support, we can expand the tuple, swizzle it. So if we wanted to do we have name to ID and we want to get ID to name, expand the tuple, swizzle it, and put it in a map. We preserve the reference semantics, like that's a constant ref, L value ref, and the result of the zip result is an R value ref. So error handling, yes. Who had the monads? Question about the monads? Yes. So there's a way for us to short circuit. We have this thing called unwrap optional. So unwrap optional will short circuit, and it'll wrap the entire result in an optional. So, because what I realize is, kind of the rest of the pipeline is what you can bind to, right? Like you can turn that into that. So we have our values. So we have values. We unwrap the optional. We get a string. We parse it, and we may get another optional out of it. We're going to unwrap that optional, accumulate, and that's an integer. And none of these had to deal with optionals, right? Like everything is safe. And then at the end, like because we call unwrap optional, we wrap it all back up in optional and return it. So that makes like monadic error, so we don't need to use exceptions, because otherwise with ranges, like when you're iterating, if you have an error, like what are you going to do, throw an exception? This one allows us to just use it kind of almost transparently, put it in there.
And if the error happens early, the optional just flows through and pops out back.
The optional pops straight back up. Like we don't even hit the lower stages. Like we bail early. And we can have monadic style, so C++23 added and then transform, and then in transform to std optional. This is a very verbose way of doing this, but you can do like unwrap optional and transform completes, using that, with the complete thing, so it does the same thing. And we all, go ahead.
If I call unwrap optional and then 2, so
Like 2 vector?
yeah, 2 vector.
So we'd end up finally getting in, the result would be std optional vector int.
Which will be shorter than whatever came in because
Yeah.
skip.
And then we also have support for doing it with statusor. So statusor is like the abcell, monadic error handling thing. So say we have like a statusor vector of strings, and we have a statusor parse int. So our values, we have a statusor vector of string. We unwrap statusor complete. It's a complete value, right? So we call the unwrap complete on it. We get std vector. We transform each element. And passing a string, that gives us a statusor int. We unwrap it, we transform it, we convert it to a vector, and then this rewraps it again into statusor vector int.
And that's because of the constructor of statusor at the return, the result at the end.
At the end, that's even if you put auto here, it'd still work.
I see. So it's just because of the use of unwrap statusor.
Unwrap statusor, because we have access to the whole pipeline, unwrap statusor can actually wrap the whole thing there. All right.
Basically,
Go ahead.
so only if all the elements for status, the 2 would return the status, right?
Right, but now everything is an int, so it just
some of
would.
them are status, and some of them are like square integers, like integers. Then 2 will just return the vector of integer.
Right, and we break early on the first error. Like we're not filtering them. So higher order status, we can T stuff. So we can have T, which gives us a tuple of all the results of everything, and we can pass like a compose element there. So we can do min, max, and count, right? So we don't need an std min max, right? We can T, max, count. We can do everything in one shot.
So T always goes down all the other avenues.
Like everything that gets passed each element that T receives, it passes it down each of its elements and stores it as a tuple as the final result. We can group elements. So let's say we've got a list of employees, and we want to hey, only the full-time employees, the count of each organization by the number of full-time employees. We can do map group by. So map group by uses like a associative container like std unordered map, absolute flat hash map, anything like that, and we tell it what we want the key to be, the org, right, and then we can pass in a list of stages that it'll do with each element of the group. So it'll filter and do a count. Oops. And then it will do a make pair, and then output an STD vector. With the reference inputs, by default, like if you don't pass in anything, it does constant ref. For L value references, it keeps them as const. So you end up with, we don't copy the values, and we end up with constant STD unique pointer ref for the elements. We can opt in to make it immutable by putting an STD ref, and then we get the mutable. And then if we move them, each element gets R value. And we also have some nice conveniences, stuff that have been bothering me, like how do you initialize an STD vector with unique pointer? So this line doesn't work because, anybody know why it doesn't work?
Initializer lists are constant.
Yes, initializer lists are constant, so we can't actually move out of it. But you can apply braces as make unique int to STD vector.
How did you do that?
It deduces as an array. So we can move elements out of the array. But it's painful enough, like I did, like, why don't we just do it, just fix it. The other thing is moving keys out of a map. So the first one doesn't work, right? And people might get clever and try the second one, and it still doesn't work. Anybody know why it doesn't work? Well, why doesn't the second one work?
What's the type of S?
S is a set. Keys are const, right? So moving and const R value copies apply automatically when it's moving out of, it'll use extract to get the correct R values out. Go ahead.
The previous slide, how do you deduce the size of the
Yeah, good question. The question was, how do we deduce what that was? Instead of using an initializer list, we reduce it as a R value reference to an array.
How do you deduce the size? Can you template the size?
Yeah, we can deduce the size on the template as well.
Does it work?
All right. So going back to our challenge, right? Given a text file and an integer k, print the k most common words in the file and the number of occurrences in decreasing frequency. So let's create some stages. So let's create read lines, right? So we take an iStream as a complete, and it's a complete transformation. It's going to be complete to incremental. And we're going to return complete to complete. We're going to return a generator. We're going to return a generator that its thing is it does std get line and moves and does the output to the line. And notice we are doing, we're keeping the line around just because we can buffer so we don't keep on reallocating. Like once we read the longest line, we don't need to reallocate again with std get line. So that's our generator. And then we want to split the strings. So our transform takes a string view. Again, this is safe because we're all in the context of a single function call. And then what we do is we return abcel stir split. We call abcel stir split, which returns an iterator. And then we compose that with a flatten. So we get each word or each word out of the line using abcel stir split. And then we want to lowercase the string, right? We could just call it, or we're going into this, so let's just write it. So we take S, transform std to lower to string. Return the value.
Could you transform in place?
What is it? We're getting a std string view. I didn't transform in place because part of it is we're actually not allocating strings from the abcel stir split. It's outputting string views, so we're just using this. And then for, we did, stir split, lowercase the string. How do we get the unique counts? We can do map group by, std identity, that's our key, and count. And then that'll give us key value, right? But for sorting purposes, we want it the reverse, right? So we want count and string. So we do a swizzle and a make pair. So this is our word scout pipeline. We take in the input, whatever the input stream is, read lines, split string, lowercase string, unique counts, put it in a vector, partial sort it for the k elements because we only care about the top k. We take k, expand the tuple, and output. Right? And we minimize the number of times we return, so we minimize our dangling references, and we do this all inside the safety of apply. Thank you. Any questions? Go ahead.
And so when I asked about the availability, you said there needs to be some type of business case or some type of like upheaval from the public masses or something, but what would actually be a beneficial thing to do? Because I will tell you, if this were there, I'd use it. I mean, I have two specific reasons. One, I have something that doesn't, I mean, it's very scary how similar it is. It's a different use case, and for something different. But I don't use ranges for the specific reasons you talked about earlier, and a couple more things. But I also personally happen to, don't kill me, I think iterators are the most dangerous thing in the language. They're worse than raw pointers because people can hold a reference to it and the stuff goes away, and most people don't even know the reference invalidation rules for iterators, and so it's really, really scary. So something like this is I would definitely use that.
Yeah.
I really, really like it. But so what's the use? I mean, what is the policy for? Is there just feedback giving to somebody?
I'll pass on the feedback.
I mean, the easiest answer is if you're a Google Cloud customer,
Yeah.
tell your business partner at Cloud that you want it. That's the easiest answer.
Yeah. Are there any other questions? Go ahead.
Yeah, so read lines was complete to incremental.
Yes.
Why not incremental to incremental?
Let me see. Actually, no. Read line. Why not incremental to incremental? Because this one here, right?
Yeah.
The first thing, the first argument for the apply is always like a complete thing, right? So we're working on we're taking in the std sin, right? That it's processing read lines, and that's the whole thing that it's doing, right? And we don't want to just iterate std sin, right? Like we can't iterate the iStream, and we'll get the wrong things out, and we want to get the get lines. That's a good question. If we had something like some languages have like dot lines or something, we can do it. Anything else? I saw another hand there.
Would it be possible to implement this with the ranges v3, the word count, and did you compare?
I did not compare. The ranges, yeah, you could. I did not implement with ranges v3. I think it'd be a little bit trickier just because we're doing some stuff that is kind of iffy, like returning we're taking a string view and returning iterator, something that refers to that. Like doing it without the protection of apply would be kind of like living dangerously, and especially with the return stuff. Like I think in there's a good chance if you translated this directly to an iterator model, you'd have something dangling somewhere. Go ahead.
Okay, can you explain why the stack grows cubically in the standard library implementation of piping and all that stuff?
Yeah, so basically for this, I think it's code defined. All right, so basically, I think we had each thing kind of holds a little bit of the one before it. So we hold we had to hold the previous iterator, and we had to hold the transforming function. And also, I believe we also hold we also cache begin too, because I think begin is supposed to be constant. So we had to cache the begin iterator. So we end up holding multiple iterators in each
That
thing.
was my previous question.
Yeah.
Whether this is a consequence of the cache or is something more fundamental. Because the cache is not fundamental, in my opinion.
Yeah, you had a cache. Otherwise, you get amortized constant time. I think you get it. Maybe we could get it down to n squared instead of cubic. And part of it is because it has to hold the one in front of it. There. And there's also talk like maybe you could, if you're smart, you could probably
I see. Yeah, so like,
because of the way you're composing, right? This one, we don't. Rappel doesn't need to hold the one in front. It just knows about the one in front because it's just a sibling of it, right? Like it's part of the same tuple. This one actually encapsulates the one as we go along, right? And if you were doing like Java or something with like garbage collection, we could just hold a pointer, right? Because we don't have to worry about leaking references. But if we just hold a pointer to the one, like we make the potential for like for dangling references even worse. Any other question? Go ahead.
I maybe didn't catch it, but do you need to do something special if you want to short circuit some of the loops? Or
So in there's that done thing. So each stage, like the stage impl has a thing where it's done. So this automatically checks if any of the stages are done as it's going through. So it'll short circuit. You don't need to do anything to short circuit.
so
You could
everything has a flag.
Not- not.
Information has a flag.
Yeah, it does. It checks the thing as it goes down, as it at the top level goes down checking, and in the implementation, and that's where we can use take to actually short circuit everything. So it short circuits. It short circuits basically up at the top, where we do the transform from incremental to complete. Any other questions? Go ahead.
Yeah, I think you focused a lot on the safety for Rappel, and then was there any like tipping point to like conceive this project, or I just went through.
Sure. So there was a tipping point because there was so STD ranges, like there have been other libraries that have implemented this type of composition before STD ranges, like Range v3. There's CPP Iter tools, and there were some internal ones at Google too that kind of implemented using the pipe iterator. And internally, I answer a lot of questions for my team about like C++, if they have crashes and things or compiler errors and things. And I got tired of getting called about the leaking references from like where you have the temporary to that one. And there's some points where it can actually kind of result in a compiler error, or else it leaks. And you could like ranges has something called it's a known enough problem that ranges has something called cache one. I think it's ranges view cache one, the little cache one thing, and kind of you had to sprinkle it correctly as a magic incantation in the correct portions of your thing. And I got tired of like telling people to do that. And I was like, all right, and then the questions with the Stack Overflow potential. And I was like, I never want to answer that question ever again. So let's look at doing this.
does the name Rappel mean anything?
It's a synonym for Absel. Yeah, and so it started out with a horrible name called Output Combinators, and then we were looking for like namespaces and stuff, and like it became Range Pipeline Library, so RPL is nice and short, and then, hey, Rappel turns out to be, RPL is Rappel, which is a synonym for Absel.
Can you talk a little bit about the adoption inside the different Google teams, and like what the main driver and how will people usually migrate from free ranges code into Rappel without going through ranges, or if there's an existing code base, how do you migrate?
Sure. So part of it is like we've actually embraced Rappel, and like internally, like in the C style guide, like we actually don't allow uses of STD ranges, and that was a concern going on for like a while now, like even before Rappel, like with C++ 20.
It was never allowed.
It was never allowed. We knew with C++ 20 is like, what should we think about? And like that was one of the reasons, why I think Rappel was embraced by the larger group inside Google. It's like, this is, a way to provide it. And so people like making pipelines, right? So people are doing this. For our group, like we used to use the previous ones, like we've been converting it, and like people are liking it because, hey, it's crashing less, right? Like if there's a place that's, it had crashes there, and like people are like, hey, why not just, instead of trying to debug this, I'll just convert it to Rappel. So it's been kind of incremental going on.
Do you think that ranges can be amended sort of to support these idioms, or is kind of?
I think it's a fundamental problem of like choosing to base your transformations on iterators. Like iterators are super flexible. They're awesome, right? But because they're so flexible, like you can use, all you need in your toolbox is a screwdriver, right? You can use a screwdriver as a hammer, you know? But if we keep on basing on ranges, because it's like if you look at like with the dangling stuff, they're going to to preserve that flexibility that the laziness gives you. Ranges is going to extraordinary lengths in terms of like typing and trying to be able to convert R values into dangling references types and try to catch stuff at compile time. But I think it's fundamental to you have the lazy one at a time issue, right? And I think these are kind of fundamental to it, and you kind of had to switch gears. I mean, could there be something based on this that's more standards? Yes, but I think a lot of these problems are inherent in the laziness of iterators, right? I mean, that's just what what you're given.
Do you think there is a kind of a reduced scope for ranges still where it's safe to use, like, let's say, ranges that only works for input iterators or something like that, some category of iterators, or remove filter, which is kind of the...
I mean, I think iterators should be iterators in that they access elements, right? Transforming elements, I think maybe, in a lot of cases, a different paradigm, something like this, like along the algorithm thing should be right. Like the original STL was like that, right? Like we had iterators for like accessing all these things inside, like a vector or list or whatever. And then we had the algorithms that were eager that did the transformations, right? And we kind of shifted from that to pushing everything on iterators, and I think, that's led to some issues. Go ahead.
So the monadic stuff was really cool to see. It's pretty awesome. I had a question. So if you want to mix and match different types, so say you have some functions, some stages that might use either, or your version of either, and some optional. Is that something that's possible? Like you want to have nested stages along those lines?
Oh, in there right now, it would be possible. Right now, we haven't supported cross monadic composition, like an optional and a status or you could do it. The mechanism I think is flexible enough to be able to do it. We just haven't done it. But you could do it. But let's see.
Because if you have existing state functions you want to use, which might have certain monads.
Yeah, you could do that. There's ways to extend this, but like I said, we haven't. It's on my thing. Maybe combining monads, but then that becomes very specific, right? Any other ones? Thank you very much.